Hi students, in the previous classes we have discussed the tangents and normals of the circle. In this session we are discussing the chord of contact of a point with respect to the circle and pole and polar of a point with respect to the circle. Now in this session we are discussing the chord of contact and pole and polar of a point with respect to the circle. Okay. So what is the chord of contact of a point with respect to the circle? First of all, look at the diagram. So it is easy to understand the concept. So, so this is the circle. What is the chord of contact of a point P of x1, y1 with respect to the circle? What is the chord of contact of a point P with respect to the circle? First, draw the tangents to the circle. Draw the tangents to the circle. They meet at capital A and capital B. These tangents touches the circle at these 2 points capital A and capital B. Now join the chord AB. This chord AB is called the chord of contact of P with respect to the circle. So this is the chord of contact of P with respect to the circle. This is the concept of the chord of contact of a point with respect to the circle. See this definition. If the tangents drawn to the point P of x1, y1 to the circle S is equal to 0 touches the circle at capital A and capital B, then the secant AB is called the chord of contact of P with respect to the circle. So this is the concept of the chord of contact. Okay. See the theorem. If P of x1, y1 is an external point to the circle, S is equal to x square plus y square plus 2gx plus 2fy plus c is equal to 0, then the equation of the chord of contact of P with respect to the circle S is equal to 0 is S1 is equal to 0. This is the theorem for finding the chord of contact of P with respect to the circle. That chord equation is S1 is equal to 0. Now we are proving this theorem. See the theorem. So what is given? Given that the circle S is equal to x square plus y square plus 2gx plus 2fy plus c is equal to 0. This is the given theorem, and the given point P is x1, y1. Now we have to find the chord of contact of this point P of x1, y1 with respect to the circle. Look at the diagram. This is the circle. Now this is the given point x1, y1. Draw the tangents from P to the circle. They meet at capital A and capital B. Now the line joining AB is the chord of contact of P with respect to the circle. That is the definition. Now we have to find the chord of contact equation. AB is S1 is equal to 0. Now we are proving that the chord equation is AB is S1 is equal to 0. Okay, so this is the given point x1, y1. Draw the tangents from P to the circle PA and PB. Now the joining the line AB is called the chord of contact of P with respect to the circle. Now we are proving this chord equation AB is S1 is equal to 0. Okay, that is our proving result. Now we are taken the meeting point is x2 y2 and b point we are taken x3 y3. We are taken x3 y3 are the meeting points of the circle. Okay, now first draw the tangents. Draw the tangents from P of x1 y1 to the circle S is equal to 0. They meet at A of x2 y2 and B of x3 y3. These are the 2 points meet at the circle. Okay. Now we are writing the tangent at A of x2 y2 and the equation of the tangent at B of x3 y3. Now we are writing the tangents. Now the equation of the tangent at A of x2 y2 to the circle S is equal to 0 is S2 is equal to 0. What is the equation of the tangent at x1 y1 to the circle S is equal to 0 is S1 is equal to 0. For x1 y1 we are writing the tangent is S1 is equal to 0. But here the point is x2 y2. At this point the tangent equation is S2 is equal to 0. Now we are writing S2. What is S2? Xx2 plus yy2 plus g into x plus x2 plus f into y plus y2 plus c is equal to 0. This is a equation 1. Now again the equation of the tangent at B point at B x3 y3 to the circle S is equal to 0. At this point x3 y3, what is the tangent equation? S3 is equal to 0. Now we are writing the equation of the tangent at x3 y3 to the circle, that is S3 is equal to 0. What is S3? X3 plus y3 plus g into x plus x3 plus f into y plus y3 plus c is equal to 0. Okay, these are the tangents at A of x2 y2 and B of x3 y3. That is the equations 1 and 2 represents the equation of tangent at A and the equation of the tangent at B. These two tangents are passing through the point P of x1 y1. Since these two equations, since equations 1 and 2 passes P of x1 y1. Now we have to substitute this point in these two equations. Okay, now substitute P x1 y1 in equation 1 and 2. Okay, now substitute x1 y1 in equation 1. We are getting the equations x1 x2 plus y1 y2 plus g into x1 plus x2 plus f into y1 plus y2 plus c is equal to 0. This is a equation 3. And again substitute this point x1 y1 in equation 2. Then we are getting here x1 x3 y1 y3 plus g into x1 plus x3 plus f into y1 plus y3 plus c is equal to 0. This is say equation 4. By observing equation 3 and equation 4, these 2 points here, A of x2 y2 and B of x3 y3 lies on the general equation. By observing 3 and 4, the general equation in x comma y, that is xx1 plus yy1 plus g into x plus x1 plus f into y plus y1 plus c is equal to 0. By observing equation 3 and 4, this equation xx1 plus yy1 plus g into x plus x1 plus f into y plus y1 plus c is equal to 0 satisfies the 2 points a of x2 y2 and b of x3 y3. See that in this equation we have to substitute x2 y2, then we are getting the equation 3. Okay. So here substitute x2 y2, we are getting x1 x2 y1 y2 plus g into x1 plus x2 plus f into y1 plus y2 plus c is equal to 0. If we substitute the point x2 y2, then we are getting the equation 3. In this equation we have to substitute x3 y3, we are getting the equation 4. So this equation passing through these 2 points a and b. A point is lies on this equation and b point is also lies on this equation. A, b 2 points satisfying this equation. So this equation represents the line of AB. So which is the line of AB. Since these A and B are satisfying this equation, so this equation which is the line of AB. Okay, so the line of AB is the chord of contact of B with respect to the circle. Therefore, the chord of contact. Therefore, the chord of contact. Therefore, the chord of contact of P of x1 y1 with respect to the circle s is equal to 0 is s1 is equal to 0. This is the chord of contact of P of x1 y1 with respect to the circle is s1 is equal to 0. This equation represents s1 is equal to 0. What is s1? xx1 plus yy1 plus g into x plus x1 plus f into y plus y1 plus c is equal to 0 represents the equation of the chord of contact of AB with respect to the point P x1 y1. So this is the chord of contact P of x1 y1 with respect to the circle, that is s1 is equal to 0. Therefore, the equation of the chord of contact of P with respect to the circle is s1 is equal to 0. So this is the theorem for finding the chord of contact of P of x1 y1 with respect to the circle s is equal to 0, that is s1 is equal to 0. See the note here. If the point P of x1 y1 is on the circle s is equal to 0, then the tangent itself can be defined as the chord of contact. So this is the case. If the circle, suppose this is the circle, if the given point is lies on the circle, suppose the point x1 y1 lies on the circle. What is the definition of the chord of contact? Draw the tangents from the point to the circle. The meeting point joining line is the chord of contact. In this case, if the point is lies on the circle, then what is the chord of contact? So this is our note. So if the point is lies on the circle, then the chord of contact coincides with the tangent at that point. Now we are writing the secant tangents from the point to the circle. Now we are writing this is the tangent. This tangent meet at the point P. Only one point here, the touching the circle at the point P point is lies on the circle. Now the tangent at the point is meets the circle at only one point. So we are what is the chord of contact? So the tangents meet at 2 points. The meeting 2 points is the chord of contact. But here the point x1 y1 is tangent at the point. So only one tangent can be drawn at this point. So the tangent itself defined as the chord of contact. So this is the note here. The point P is lies on the circle. Then the chord of contact is coincides with the tangent at that point. So that is the note 1. Next, note 2 is if the point P is an interior point of the circle S is equal to 0, then what is the chord of contact? What is the chord of contact? See this, look at this diagram. This is the circle. Given that here point is interior point, suppose P is x1 y1 is inside of the circle. What is the definition of the chord of contact? Draw the tangents from the point to the circle. Here no tangents can be drawn from this point to the circle. Only we are write the secants only. Now we are writing the secants only. Now we are writing number of secants. There are no tangents can be written from this point to the circle. So the chord of contact does not exist in this case. So what is the chord of contact definition? Draw the tangents from the point to the circle. The meeting point points joining the line is the chord of contact. Here we are unable to write the tangents for interior point of the circle. So the chord of contact in this case does not exist. If the point is interior of the point of the circle, then the chord of contact does not exist. So this is the note observing. See the theorem. If theta is the angle between the tangents through a point P of x1 y1 to the circle S is equal to 0, then tan theta by 2 is equal to formula r by root of s11, where r is the radius of the circle. This is the theorem. It is very important for finding the angle between the tangents from a point to the circle. So see the proof by writing proof. This is the circle. This is the our given circle. Okay. Now we are writing the tangents from this point to the circle. Okay. These are the tangents from the point x1, y1. Now the angle between the tangents is theta. These are the tangents meet at capital A and capital B. This is the center of the circle. Join CA and CB. Here the line PC bisects the angle. CP bisects the angle between the pair of tangents. If the angle of APB is theta, then the angle of APC is theta by 2. This angle is theta by 2. Now what is the AC? AC is the radius of the circle. And what is PA? PA is the length of the tangent from P of x1 y1 to the circle. So PA is the length of the tangent from P to the circle. What is the length of the tangent from a point to the circle? We are already in the previous classes we have discussed the length of the tangent is root of S11. Now we have to find the angle theta from this diagram. Okay, see the proof here. What is let S is equal to 0 be the equation of the circle. Draw the tangents. Draw the tangents from P of x1 y1 to S is equal to 0. They meet at capital A comma capital B. Now what is given? Given that angle is given that angle APB, that is the angle between the pair of tangents is given theta. From the diagram, angle APC, that is theta by 2. From this diagram, here PC bisects this angle between the pair of tangents. Angle APC is theta by 2. From triangle APC, we are writing tan theta by 2. Here tan theta by 2 is equal to opposite by adjacent. What is here opposite side? AC. What is adjacent side? PA. Here tan theta by 2 is equal to AC opposite by adjacent side. Here what is AC distance? That is the radius. Here AC distance is the radius and PA distance is the length of the tangent, that is root of S11. From that here we are getting tan theta by 2 is equal to R by root of S11. Tan theta by 2 is equal to R by root of S11. From this we are finding the angle between the tangents. From that tan theta by 2 is tan inverse of R by root of S11. From that theta is equal to 2 tan inverse of R by root of S11. So this is the angle between the pair of tangents from an external point P of x1 y1 to the circle. This is the very important formula for finding the angle between the pair of tangents from an external point P to the circle. That is we are using generally we are remembering we are knowing the theorem formula tan theta by 2 is equal to R by root of S11. Tan theta by 2 is equal to R by root of S11. R is the radius of the circle and root of S11 is the length of the tangent from the point to the circle. From that we are getting theta is 2 tan inverse of R by root of S11. This is the finding the angle between the pair of tangents from an external point to the circle. Okay. Next, what is the concept of pole and polar of a circle? See the definition. Before that, we are observing this diagram. Look at this diagram. First, look at this diagram. It is easy to understand this concept. Okay. This is the circle. Okay, this is the circle. Draw the secant from an external point to the circle. Draw the secants from external point to the circle. They meet at the points here. This is A, this is B, and this is C, and this is D. These are the secants from an external point P to the circle. They meet at capital A and capital B and capital C and capital B. Now we are writing the first draw the tangents from an external point P to the circle. They meet at capital A and capital B. Now we are writing the tangents at capital A and capital B. They meet at the point suppose this is say R, and draw the another tangents at capital C and capital D. Now we are writing the tangents at capital C and capital B. They are intersecting another point S. These are the S and R are the points of intersection of the tangents drawn at the points where the secants meet at the circle. Now the line joining R and S, the line joining R and S, That is the locus of the point of intersection of the tangents. The locus of the point of intersection of the tangents drawn at the points where the secants meet at the circle is the polar. This line is S, or line is the polar of P with respect to the circle. This is the polar of P with respect to the circle. Okay, that is the polar concept. So this line is the polar of P of x1 y1 with respect to the circle. So this point P is the pole of the polar. This point P is the polar pole of the line SR. So P point is the pole of the line, and line is the polar of P with respect to the circle. This is the concept of the pole and polar. Once again, I recall the definition. Let S is equal to 0 be the circle. Draw the secants from an external point P to the circle. They meet at capital A and capital B. Then the locus of the point of intersection of these tangents is the polar of P with respect to the circle. The line is the polar of P and the point is the pole of the polar. So this is the pole and polar of a point P with respect to the circle. Okay, this is the definition of the pole and polar. Though this definition is very important, you must understood clearly. So what is the pole and what is the polar? Polar is the point of intersection of the tangents drawn at the points where the secant through capital P to the circle. That locus forms here a straight line. That straight line is the polar of the point P with respect to the circle. That line is the polar of P and P is the polar of the line. And P is the pole of the polar. Okay, this is the concept of pole and polar. Okay, so next case 1. If P point is outside of the circle, then the polar forms inside of the circle. So in the definition we are taken the point is outside of the circle. Once again I draw the figure. This is the circle. If the point P is outside of the circle, the point P is outside of the circle, then the polar forms inside of the circle. That is, polar intersects the circle. See, once again, these are the secants drawn from P to the circle. They meet at A, B, C, D. Now, the tangents at capital A and capital B intersecting points. These are the secant tangents drawn from the tangents. These tangents intersecting point locus is the polar. That is the definition of the polar. So this is the polar of P with respect to circle. Okay, so here point is outside of the circle. Then here the polar intersects the circle at the 2 points. This is the case we are observing. So if the point is outside of the circle, the polar intersects the circle at 2 points. Okay, so this is the first case. See the second case. If the point P which is inside of the circle, then the polar forms outside of the circle. In previous case, the point is outside of the circle, the polar intersects the circle at 2 points. In this case, the point is inside of the circle. See the diagram. This is the circle. If the point is inside of the circle, first draw the secants through capital P. Now we are writing the secants. Here the secants capital A and capital B, capital C and capital D. Now we are writing the tangents at the meeting point. Here A and B, we are writing the tangents at capital A and capital B. Now we are writing the tangents at capital A and capital B. Okay, these are the tangents. We are writing capital A and capital B. They are intersected at this point. Okay, so these are the tangents intersect at capital R. And another secant tangents drawn at capital C and capital D. Now we are writing the tangents at capital C and capital D. This is the tangent and this is another tangent. These tangents are intersect at this point. Okay, these intersecting points of tangents join this point of intersection of the tangents. This line is the polar of P with respect to the circle. This is the point x1, y1 inside of the circle. The point inside of the circle. Now draw the secants through capital P. Now we are writing AB is one secant and CD is another secant. Now we are writing the tangents at capital A and capital B. The intersecting points point of these tangents say capital R, and the tangents at capital C and capital D. These two tangents intersect at capital R. The point of intersection of these tangents locus is the polar. This is the polar of P with respect to the circle. If the point is inside of the circle, then the polar outside forms. The polar forms outside of the circle. In this case, the polar does not touches the circle. This is the second case we are observing. If the point is inside of the circle, if the point is inside of the circle, then the polar forms outside of the circle. In this case, the polar does not touches the circle. In this case, the polar does not touches. In previous case, the polar intersects the circle at 2 points. If the point is outside of the circle, the polar intersect the circle at 2 points. If the point inside of the circle, then the polar does not touches the circle. This is the second case. See that if the point which is lies on the circle, then the polar coincides with the tangent at that point of the circle. See that this is the case. This is the circle. Now, if the point is lies on the circle, P is x1, y1 lies on the circle. What is the definition of the polar? Draw the secants. Draw the secants. They meet at the circle at some points. The tangents at their points of intersection is the locus. That locus forms a polar. Now here the point is lies on the circle. Now we are writing number of secants. Number of secants. So these secants passing through capital P. In that case, so at the point of intersection of the tangents at the meeting point. Okay. So these are all lies on the tangent at P of x1, y1. So that is the case. If P point is lies on the circle, then the polar coincides with the tangent at that point. So in this case, the point P is lies on the circle. The polar is itself defined as the tangent at that point. So the polar is coincides with the tangent at that point P of the circle. This is the third case. Next, fourth case is the point if the point is the center of the circle S is equal 0. The point is the center of the circle S is equal 0, then the polar of P does not exist. See the diagram. This is the circle P, this is the center. Now if we take the point is at the center, that is P is equal to C. Now we are draw the secants through capital P. They meet at capital A and capital B. Now we are writing the tangents at capital A and capital B. The point of intersection of the capital A and capital B is point of intersection of the locus is the polar of P with respect to the circle. That is our polar definition. So now we are writing the tangents at capital A and capital B. We are writing the tangents at capital A and capital B. These tangents are parallel to each other. Since see here AB is the diameter of the circle. So if any secant through capital P, here P is we are taken the center, taken at center. So if you take any line through P, any secant through P, that is the diameter. So at the diameter, the tangents are parallel. The tangents are parallel to each other. So these tangents are not intersecting. In this case, the tangents drawn at the points of intersection of the secant through capital P are parallel. These tangents are parallel. So there is no point of intersection of the tangents. So in this case, the polar does not exist. So in this case, if the point is taken at the center, there is no polar. Here the polar does not exist. Okay, so this is the fourth case. So what is the fourth case? If we take the point P at the center of the circle, the polar does not exist. Okay.